In this video, I want to introduce our first method for storing programs. What this is going to be called is the contiguous memory method. So the idea is this, right? We're going to say that the simplest way we could store a process in memory, store a program in memory, is to store it contiguously. Now what contiguously means is that we're storing things like back to back. So to draw a little picture here, maybe I have my main system memory, and I have this thing here, right? That's all my RAM. And I have it, maybe I could even say it's broken into chunks. We'll end up talking about this a little bit more. So I have made 4 chunks here. What contiguous means is that if I have a process, that process is all stored back to back. So for example, process 0 might be here. The other spaces, right, could be empty. They could even have something else. Maybe I can add a P1 over here. The point is, right, that P1 is contiguous. So it just has one place in memory, and everything that makes up P0 is all in that kind of little spot there. So it's not, there's not any, P0 over here, right? That's completely something different, right? That's kind of a different model. Right now, we're just going to say that everything is kind of kept together. So this is what we call a contiguous model, right? There's kind of a contiguous amount of space that is used by the process. Now, the word contiguous, basically, it's similar basically to the word continuous, except that it's for when something is discrete, right? So normally continuous is like for something like a real number. This, because we're going by numbers, right, whole numbers, something looks like an integer, we say it's contiguous, right? So it's continuous from some index to some other index. So this is our basic model. In here, right, what's kind of implied is that we're going to know 2 things. First of all, we're going to know where my processes start. So over here, right, that's kind of my starting place. And that will be called our, it'll end up being stored in something called the relocation register. Basically, it's going to be some sort of a base, right? And I think I'll just go base for now. We don't need to worry about register names too much here. So this is the base. Also, what we know is what is called a limit, right? So if I write over here, I'm going to write in limit. Basically what we're saying is I'm going to know how much space a particular process should need. Now here, what I'm trying to do at the end of the day, right, is basically bound the process and say, okay, this is the space it's illegal for this process to work in. And here, right, it's really simple for me to do because if I have a contiguous model, well, I start somewhere, right, my base, and then I go only so far, right? I have a limit. I don't have to worry about P0 existing anywhere else. If I just have these 2 things, base and limit, then I know what exactly is the working space for my process. And that's useful for a whole bunch of things, right? It's useful for security, right? Making sure our process is only editing its information, right? Also for allocation, right? Knowing that I'm going to reserve memory that doesn't overlap with somebody else. So it's very straightforward to do here. So that's our basic model. Now for a few more details here, right? What happens is in the picture before, and I guess I'll duplicate a little bit. So whenever we have our overall system memory, this thing is actually going to be divided into 2 regions. And I'll just kind of arbitrarily put this here. I don't have a real reason for putting it where I am putting it, that little division there. This is basically where you say user space versus, I'll just go system space. So the note here somehow is that my RAM, right, when I have this huge memory collection, right, I'm going to have a space that's basically for programs the user is running, and then also a space for the programs the operating system is running, right? And I'll kind of divide in half. This is kind of the way things work. A question for you guys is though, why would we do this? Why do we make it this clean division? So think about that for just one moment. So if you think about it, right, the main reason is going to be security. So what we can say is anything in system memory should be protected, right? So there shouldn't be any reason for something that's like a user program to go into the system's memory and change something, right? Because that memory belongs to kind of key processes that are running. It doesn't make sense for a user level process to go and be like, oh, I need to change something in here, right? That's kind of on the other side. So we have sort of this firewall almost, right? It's a little, barrier here, right, to stop, user programs, which could be anything, right? It could be something that you download from the internet from accessing the memory that's assigned to programs that really are, belong to the operating system, right? We don't want that to happen. So that's kind of one way, right, this whole thing will be set up. Now to go down here, right, there's a little bit more notes here. We talked earlier about this idea of a base and then a limit. And the base, right, is stored in this thing here called a relocation register. And the limit is also stored in this thing here called the limit register, which kind of spans across 2 lines, so it's awkward to draw a circle around, but okay. So yeah, the idea here, right, is that if a process is running, right, what I'm going to do is I'm going to reserve 2 registers on the CPU, right, a relocation register and a limit register, and that's the place I'm going to store those magic values, right? So if I have my process over here running, right, I have basically my base and then my limit. I'll go base, limit. Those 2 things end up being mapped to 2 registers, right? And when we move processes back and forth, when we do context switching, those 2 registers are things I'm going to have to keep track of in the process control block, right? So I'll kind of record those, right? And I do my context switch, I need to either save those or load those or whatever. Those are going to be kind of key things I need to track, right, so that I can know what it is that the process is actually doing, or where is it actually working. So I'll have those. All right. So let's say, right, the program is running. What happens next? The program, right, maybe makes basically a request, right? Maybe it makes a read, maybe it makes a write. And what happens, right, is we have this overall kind of flow chart that is acted upon. And we'll see this, in a few different places, right, this idea of this flow chart here. What this is, right, is kind of the overall process of how do I figure out what I'm supposed to do, right? How do I do my memory lookup? So let's suppose for a second that we're doing a read. What happens? So initially, right, you have your CPU, right? Your CPU executes some instruction. This instruction, wants to read something. Okay, fine. Initially, right, it's going to have something that looks like a logical address, right? It's going to have basically an address in terms of just the process itself, right? It's not, in terms of the global memory. It's just in terms of the process itself. So what do we do? First thing we do, right, is basically check to see whether it's kind of within the limit, right, of the process, right? So the process is only allowed to access a certain part of memory, right? Is it within that limit? If it's not, well, then I have an issue, right? I have an issue, right? This process is basically trying to, right, it's trying to access memory it's not allowed to, right? And so I want to kick it out. And so the note here, right, is that, if I exceed my limit, right, I want to basically trap that, right? So I'm going to have some sort of interrupt, some sort of exception to basically trigger that and say, this is an out of bounds here, right? And that's something maybe you guys have seen, right? If you run a program, sometimes you'll be like, oh, this program has an invalid memory request, right? That's kind of one of the issues that you can get from this, right? Is you're trying to access something you're not allowed to. So yeah, let's say that happens, right? So let's say this is, and I should put a note here. We'll say this is, process of, using memory is really what this diagram is showing. So let's say, right, we're halfway through there, right? We verify that we're within our limit, right? So we're not, outside of our bounds, right? We're not, trying to go over here, right? We don't want that. We're where we want to be. What happens next? Well, if we're inside of our little domain, right, that's good, that's assigned to us, then basically we just add the real allocation register to the logical address, and then from that we get the actual physical address. Okay, so you can see here, right, over here, right, this is a decision to figure out, is this good or bad? Do we want to allow this memory read? And once we do decide to allow it, well, then we have to actually compute the address, right? So then we do our little computation there, and from that we basically map, our logical address to our physical address. So that's our overall kind of flow here, right? Is we have our logical address basically being sanity checked and then being converted into a physical address. Now we'll see these charts a few different times, but here basically you can think of this as being kind of the simplest version, right? So later on, right, we'll have kind of a lot more steps in between because there are maybe more levels of indirection. For now, this is pretty straightforward. So there you have it. That's kind of an overview of contiguous memory allocation. It's the kind of simplest scheme. There are some issues with it, which we'll eventually address in some future videos.